Our next speaker is Oana Lazar. She's embedded software engineer at Tessent Embedded Analytics, part of Siemens EDA, and she got a master's degree in electronic engineering from the University of Southampton with a specialization in mobile and secure system. Press the right arrow.
Sorry?
Yes, just press the right arrow or this one.
Yeah, that's fine. Yeah. Sorry. Thank you, Jérôme, for the introduction. Welcome, everyone. My name is Oana, and today I'll be sharing our journey and approach for designing a new debug and trace solution for RISC-V systems. We'll begin by breaking down the title of the session, delving into the various components of the debug approach, which includes highly efficient trace, minimally intrusive program logging, and the benefits of our approach, and then closing with a remark on system verification. We are fortunate enough today to live in times where the complexity of RISC-V applications is skyrocketing, with exciting use cases that we've seen over the conference, such as generative AI, high-performance computing, and multi-chiplet technologies hitting the market. However, this is both a blessing and a curse, as an increase in complexity of hardware and software leads to increasingly complex bugs. These bugs are difficult and expensive to reproduce and resolve, with issues such as silent data corruption and timing-sensitive Heisenbugs showing that the tools we currently have today aren't enough. Indeed, current solutions can interfere with both programs' timing and execution order of instructions. This can cause the debugging tools themselves to get in the way of finding these bugs, or worse, the tools simply don't provide enough depth of visibility to begin with, causing developers to hit a brick wall when debugging. This all comes at a time when skill shortages are the #1 issue across the semiconductor industry worldwide, according to the Global Semiconductor Alliance. There is therefore a demand for a different type of debug solution, one which is able to provide a combination of multiple debug methods and insights to render such complex issues easier to debug. A typical debug and trace solution uses hardware for debug control and trace collection, as well as for off-chip communication, and software for interfacing with a user environment and debugger, such as GDB. Each of these points comes with its own set of decisions. How should trace information be collected? What kinds of wired connections should be used? Which debugging environments should be supported? When navigating this, our primary concern was, how can we make this generic solution scalable and configurable for any user's needs, while supporting users in benefiting from RISC-V's ecosystem's immense potential for customization? To this end, we chose a hardware-software co-design approach. This means that at each of these decision points, we designed both hardware and software together, ensuring that each feature would either leverage the speed of dedicated hardware or take advantage of the low cost and footprint of software, all while keeping the user at the center of our decisions. This means that we also added extra hardware and software features, providing users with different ways of debugging at multiple levels of visibility, allowing them to tailor the solution to their own specific needs. The most in-depth level of visibility in the solution is processor trace. Trace is a hardware debug feature which allows you to see and record the exact instructions that are being run by a RISC-V heart in real time as the heart is running. This is the key innovation in our solution, as it allows for non-intrusive tracing of executed instructions, meaning that bugs aren't hidden by timing or instruction order interference. One of the key drawbacks of trace is that whilst it delivers the most detailed view of what is taking place within the system, it can also generate immense amounts of trace. This can create a significant bottleneck for large systems, consuming all available bandwidth. This is why we leveraged our own flavor of OpenOCD, specifically designed to handle processor trace out of the box and working with the user's version of GDB to decode and reconstruct the trace on the host with support for RISC-V custom instructions as well. But what about the limited bandwidth? That special flavor of OpenOCD provides users with multiple filtering options, allowing them to cherry-pick the exact trace that they're interested in. This can help pinpoint bugs without having to wade through gigabytes of data, and more importantly, allows the users to limit the amount of bandwidth used by processor trace to just the information that they need. The hardware side of our solution is called the Enhanced Trace Encoder. This is fully compliant with the Efficient Trace for RISC-V specification, also known as eTrace, which is ratified by RISC-V International. This specification was originally donated by Ultrasoc, who were acquired by Siemens in 2020, now forming this Tessent embedded analytics group. The eTrace specification was created to provide a standardized way to efficiently encode instruction data trace while also defining the hardware interface with RISC-V hearts. Despite the bandwidth improvements offered by our filtering options, there's no way of getting away from the fact that very large and high-performance systems will just generate a lot of trace. Efficiency is therefore crucial for such systems, so we took the eTrace specification a step further with our Enhanced Trace Encoder hardware, encoding trace in a highly compressed manner. The Enhanced Trace Encoder also has options for additional hardware extensions, which users can pick and choose to further maximize compression rates. However, even with no such extensions enabled, the Enhanced Trace Encoder boasts an average compression rate of 0.2 bits per instruction. This allows for the in-depth processor trace visibility over RISC-V hearts whilst minimizing its bandwidth usage. With optional hardware extensions enabled, we see a jump in compression rates of 40%, meaning that even fewer bits are used for each instruction. You can see this jump here in our test results using the mbench open source benchmarking suite with call counter, branch predictor, and jump to cache extensions enabled. These are covered in more detail in the eTrace specification itself. The compression rate in orange is what we see with these extensions disabled, while the compression rate in teal is what we see with some of the hardware extensions enabled, with the x-axis showing the different mbench benchmarks. Of course, a lower value in this case is better, as fewer bits are needed to represent each instruction. We recognize that there's a big jump in visibility between simply run, stop, step, debug, and full processor trace. We therefore developed an additional function that sits somewhere in the middle, and we call this static instrumentation. This allows users to add logs to their code, thereby instrumenting the program with whichever custom strings and values are most useful to them at that point. This is very similar to classic printf-style debugging, but without the significant timing interference of actually using printf statements themselves, as these could otherwise completely obscure those timing-sensitive Heisenbugs. In fact, static instrumentation logs take 1 to 2 orders of magnitude less processing time to run than their printf equivalents. This can be seen on the logarithmic graph here, comparing regular printf statements in teal with static instrumentation logging in orange, with increasing numbers of parameters on the x-axis. In this case, a smaller bar is better, as it means that the method takes up less processing time and is therefore less intrusive. Static instrumentation therefore minimizes interference to program timing and flow, allowing printf-style debugging methods to still be able to catch timing-sensitive bugs, while providing a less verbose but more customizable debugging option than through processor trace. In addition to offering different levels of debugging visibility, we also wanted to enhance the overall debugging experience through additional hardware-software features. One example of this is the Direct Memory Access module, which takes full advantage of the benefits of dedicated hardware to speed up ELF file uploads to RISC-V hearts. Of course, GDB can be used to upload executable code to a RISC-V heart, but this is starting to not scale well for increasingly large and complex programs. Even though a couple of minutes shaved off doesn't seem like much, it does slow down debug iteration loops, and from personal experience, it's just frustrating waiting for this. The Direct Memory Access module therefore offers 100 times speed-ups over GDB-only solutions, cutting down on debug time. Next, we have the Virtual Console module. This takes advantage of the capabilities of software instead. It provides multiple bidirectional off-chip communication channels, but does so in software, exploiting the benefits of software multiplexing. This means that users have the option of communicating with their RISC-V hearts using multiple virtual channels, but without the cost of having to use as many pins as in hardware-only solutions. Users can therefore use these channels to interact with software running on RISC-V hearts without having to go through a process of changing, rebuilding, and re-uploading their code. The process analytic module also minimizes the use of hardware by providing run-stop-step debug control capabilities simultaneously for multiple RISC-V hearts using just a single wired connection. You would be correct in thinking that this is a lot of hardware to include within a RISC-V system, and that this would take a long time to verify, not really helping with the skills shortage issue. Indeed, a 2024 report on ASIC functional verification trends revealed that on average, approximately half of ASIC designers' time is spent on verification instead of design. This is precisely why our hardware IP modules are pre-verified. In the same report, it was discovered that approximately 75% of ASIC projects are behind schedule, which they also attributed to the sheer amount of time spent on verification. However, despite providing pre-verified IP, incorporating new hardware into a system still brings its own set of challenges for users, namely verification at the system level. To address this challenge, we provide a verification IP, which is pre-packaged with the solution. This verification IP is based on the industry-standard Universal Verification Methodology, or UVM, and consists of a set of software classes, methods, sequence libraries, and example tests. This allows customers to check if the hardware IP modules are correctly hooked up to each other and to the RISC-V hearts components, and to check if their test bench can communicate with each module, while also allowing for the same test to be redeployed at different hierarchy levels, allowing for bottom-up design of SoC subsystems. The verification IP can be integrated into the customer's own UVM test bench. This makes it easy to quickly verify that our hardware IP modules are correctly implemented within any given RISC-V system without taking up all of the designer's valuable time. This all comes together in a complete end-to-end solution for RISC-V debug and trace, which we've named UltraSlite 5. This includes all of the hardware IP modules that we have covered, helping users to debug their code efficiently and in depth, and allowing them to spend more time on designing rather than debugging. The solution supports multiple industry-standard off-chip communication options available over a single wired interface. A dedicated software suite also allows users to determine how best to leverage the hardware options to suit their specific and unique needs. This is accessed by familiar freeware and open source interfaces such as GDB, OpenOCD, and VS Code, which also helps minimize the learning and ramp-up times before users can start to actually benefit from the solution. All this with minimal overhead due to the pre-verified silicon-proven hardware IP modules and a UVM system verification environment, all coming together in a comprehensive and efficient hardware and software debug and trace solution. If you're interested in learning more about this technology and the uses of the solution, you can view a recording of yesterday's keynote and demo presentation once these are up on the RISC-V website. And if you're specifically interested in the enhanced trace encoder, please come back to this room after the break to hear from my colleague Marcel Zach. If you'd like to hear more about UltraSlite 5 in general, we'd love to meet you at our booth, which is just outside and to the left, as well as our poster on the floor above us, also to your left. For now, many thanks for listening, and if we have any time, I'd love to hear your questions. Thank you.
We have 1 minute for questions.
Yes.
So I guess that's one question. I can see her hand here.
Hi, thanks very much for the presentation. Are your changes that you've made going to go upstream into OpenOCD?
I don't believe we've reached a decision about that at this point, but we'd be happy to discuss that with you at our booth.
Maybe even a second question. So no further question. So as you showed in the slide, you have a poster tomorrow, and you will be on Siemens booth right on the exits of this amphitheater.
Yes.
Thank you, Anna, and thank you for meeting the time.
Thank you, Jérôme, for